Welcome to my channel. In this video, we'll study what is called residue and how to calculate residue of a function f at isolated singularity. Now to define residue, we require Lorentz series expansion. So just to recall Lorentz series expansion, if z0 is an isolated singularity of a function fz, then we have the Lorentz series expansion of fz about z0 as fz equal to summation equal to 1 to infinity a minus of n z minus z0 power minus of n plus n equal to 0 to infinity a n z minus z0 power n and 0 less than z minus z0 less than r, that a n, the coefficients, can be determined from this expression for n equal to 0 plus minus 1 plus minus 2 etc. Where C is a circle with center z0 and radius less than r. Now, the first part in the Lorentz series expansion, that means the part containing the negative powers of z minus z0, is called the principal part. So this is the principal part, and the part containing the positive powers of z minus z0 is called analytic part. Now, if we explicitly write the principal part, then we'll say it is a minus of 3 z minus z0 power 3 plus a minus 2 upon z minus z0 power 2 plus a minus of 1 by z minus z0 plus the analytic part equal to 0 to infinity a n z minus z0 power n. Here the residue of the function f at the point z0 is defined as the coefficient of 1 by z minus z0. We denote residue of f at the point z0 as res f z0. So it is defined as a minus of 1, that is the coefficient of 1 by z minus z0. It is also defined as a minus of 1, that means 1 by 2 pi I integral over c fz dz. Now, here we have a very important point to be noted. Now, if z0 is a removable singularity, from the definition of removable singularity, we have seen the principal part of the Lorentz series expansion about z0 contains no term. So, if z0 is removable singularity, we can write principal part of Lorentz expansion about z0 contains no term. So, the coefficient of 1 by z minus z0 is 0 because principal part contains no term. So here we can see, so whenever z0 is a removable singularity, then the residue is always 0. Next, let us take an example. So if I take fz equal to sine z by z, z equal to 0, then isolated singularity. Now if we expand sine z, we'll see is z minus z cube by 2 factorial plus z power 5 by 5 factorial and so on divided by z. And here we get 1 minus z square by 3 factorial plus z power 4 by 5 factorial and so on. So here we can see the principal part contains no term. So z equal to 0 is a removable singularity. So we can see the residue of f at the point 0 is 0. Next, let us take fz equal to e power 1 by z. So z equal to 0 is an isolated singularity. Now, if we expand e power 1 by z, we'll see it is 1 plus 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube and so on. So, what is the residue of the point f at the point 0? We can see that is the coefficient of 1 by z minus 0. So, which is equal to 1. So, here the coefficient is 1. If z0 is a pole kind of isolated singularity, then how to find residue? So, the first technique is to use the definition of residue. That means here we can compute the Laurent expansion of the function fz about z0, and here we can identify the coefficient of 1 by z minus z0, that is, and identify the coefficient of one by z minus z0, that means a minus 1, which is the residue of the function f at the point z0. Now the second possible technique is we use technique 2 whenever z0 is a pole of order 1. That means if z0 is a simple pole, then what is residue? Then we can calculate residue as limit z tends to z0, z minus z0 into fz. Now let us try to prove this statement. So as we have already seen, if z0 is a simple pole, that means a pole of order 1, then in the Laurent series expansion of fz, there is only one term present in the principal part. That means we can write fz as a1 by a minus of 1 by z minus z0 plus the analytic part So here we need to determine a minus 1. So let us multiply z minus z0 on both sides and we'll get plus 0 to infinity a n z minus z0 power n plus 1. Now if I take limit z tends to z0, we'll get equal to a minus of 1, because as z tends to z0, this tends to 0. So this is our residue of f at the point z0. Now here we need to take limit because z0 is a singularity of fz. So fz0 is undefined. That is why we have to take limit, and we can get a minus 1, that means the coefficient of 1 by z minus z0, which is our required residue. So whenever z0 is a simple pole, we can compute residue of f at the point z0 by this expression. So let us take an example. So if we have fz equal to e power z by say z minus of 1. So here we can see the function fz can be written as phi z by z minus 1 power 1, where phi z is equal to e power z, which is analytic in the neighborhood of 1, and phi of 1 is equal to e, which is not equal to 0. So here we can conclude that z equal to 1 is a pole of order 1, that is a simple pole, is a simple pole. So whenever we have a simple pole, we can calculate the residue using technique 2. So residue of f at the point 1 is given by z tends to z0. Here z0 is 1. Z minus z0, that is z minus of 1, into fz. So here fz is e power z by z minus 1. So here we are getting z minus 1 cancels out and we are getting e. So e is the residue of the function f at the point 1. Now we have technique 3. If z0 is a pole of order n. So if z0 is a pole of order n, then how to calculate residue? Then we can calculate residue as z tends to z0, 1 by n minus 1 factorial into n minus 1th order derivative with respect to z of z minus z0 power n into hz. So we have to compute this expression to get residue of the function f at the point z0. Now if n equal to 1, that means if z0 is a simple pole, then technique 3 reduces to technique 2. That means residue of f at z0, we are getting limit z tends to z0, 1 by 0 factorial, that is 1, and d0 dz0, that means 0th order derivative, that means the function itself. So it is z minus z0 into fz. So it reduces to technique 2. Now let us take an example here. So if fz equal to 1 by z minus of 1 into z plus 1 whole square. So what are the singularities of the function fz here? We can see z equal to 1 and z equal to minus 1 are the singularities that we can determine by equating this to 0. Now, if we write fz as 1 by z minus of 1 by z minus of minus 1 whole square, that means if we consider this to be a function phi 1z, which is equal to z minus of 1, which is analytic in the neighborhood of minus of 1, and phi of minus of 1, phi 1 of minus of 1 equal to minus of 1 minus of 1, that is minus of 1 by 2, which is not equal to 0. So here we can see, we can conclude that z equal to minus of 1 is a pole of order 2 or a double pole. So if z0 is a pole of order 2, then we have the residue in this form. So here n is equal to 2, that means it is a pole of order 2. So if we want to calculate residue, we'll get for n equal to 2, this limit z tends to z0, 1 by n minus 1 factorial. So limit z tends to minus of 1, 1 by 2 minus of 1 factorial into d2 minus of 1 dz2 minus of 1 z minus of z0, that is z plus 1 whole square, into fz. So our fz is z minus of 1 into z plus 1 whole square. So if we simplify this, we'll get z tends to minus of 1. So 1 by 1 factorial is 1. And here it is d2 minus 1. So it is d dz of 1 by z minus of 1. So here we are getting limit z tends to minus of 1. It is minus of 1 by z minus 1 whole square. So the residue is minus of 1 by minus of 1 minus of 1 whole square. So it is minus of 1 by 4. Here we are getting the residue at the point minus 1 as minus of 1 by 4. Next, if I write fz as 1 by z plus 1 whole square divided by z minus 1, where our phi z, phi 2z say, is equal to z plus 1 whole square, which is analytic in the neighborhood of 1, and phi 2 of 1 is equal to 1 by 4, which is not equal to 0. So here we can see z equal to 1 is a simple pole. So whenever we have a simple pole, we have residue of f at the point 1 as limit z tends to 1 z minus of 1 into fz, that is z minus of 1 z plus 1 whole square. So here we are getting limit z tends to 1 by z plus 1 whole square, so which is equal to 1 by 4. Next, we have another technique to calculate residue of a function f if z0 is a pole of order n. So let us write the technique 4, which is for a pole of order n. So if z0 is a pole of order n, then we have seen we can write fz as phi z by z minus z0 power n, where phi z is an analytic function, is analytic in the neighborhood of z0, and the second criteria is phi z0 must be not equal to 0. Now if so, then the residue of the function f at the point z0 is given by phi n minus 1 z0 by n minus 1 factorial. That means the n minus 1th order derivative of phi evaluated at the point z0 divided by n minus 1 factorial. Now we get technique 4 from technique 3 just using this expression of fz, because if z0 is a pole of order n, we can always write fz in this form. So from technique 3 we have, if z0 is a pole of order n, then residue is given by limit z tends to z0 1 by n minus 1 factorial dn minus 1 dzn minus 1 z minus z0 power n into fz. So here if we write fz as phi z by z minus z0 power n, so it is n minus 1 factorial dn minus 1 dzn minus 1, so it is z minus z0 power n into phi z by z minus z0 power n. So here we get tends to z0, which is 1 by n minus 1 factorial into n minus 1th order derivative of phi z, that is phi n minus 1 z. Now this is a constant, so it is n minus 1 factorial into phi n minus 1th order derivative evaluated at z0. So let us take an example here. If z equal to z cube plus 2z by z minus I power 3. Here if we equate the denominator to 0, we'll get the singularity of the function fz, which is z equal to I, which is an isolated singularity. Now here we can see this can be written as phi z minus I power 3, where phi z equal to z cube plus 2z, which is an analytic function in the neighborhood of I, and phi of I is equal to I cube plus 2I, that is equal to minus of I plus 2I, and this is equal to I, which is not equal to 0. So fz is having a pole at the point I of order 3. So z equal to I is a pole of order 3. So we can use technique 4 to evaluate residue of the function f at the point I. So which is equal to phi n minus 1th order derivative. That means 3 minus 1th order derivative of phi evaluated at the point I divided by 3 minus 1 factorial. So here we require the second order derivative of phi evaluated at the point I divided by 2 factorial. Now phi z is equal to z cube plus 2z. So phi dashed of z is equal to 3z square plus 2, and phi double dash z equal to 6z. So here phi double dashed I equal to 6 times I. So our residue is given by 6i divided by 2, that is equal to 3i. Now let us take another example of essential singularity. We'll try to compute the residue of the function f at some essential singularity. Let fz equal to z e power 1 by z. So z equal to 0 is a singularity of the function fz. Z equal to 0 is an isolated singularity. So if we expand the function fz, we'll say it is 1 plus 1 by z plus 1 by 2 factorial into z square plus 1 by 3 factorial into z cube and so on. So here we can see it is z plus 1 plus 1 by 2 factorial into z plus 1 by 3 factorial into z square and so on. So here we can see in the principal part there are infinitely many terms present over here. So z equal to 0 is an essential singularity. And the coefficient of 1 by z is 1 by 2 factorial. So the residue of the function f at the point 0 is the coefficient of 1 by z, that is equal to 1 by 2 factorial, that is 1 by 2. So whenever we have a removable singularity, there the residue is always 0. If we have essential kind of singularity, to compute residue, we always have to expand the function in Lorentz series expansion, and we have to identify the coefficient of 1 by z minus z0. Next, we have a very important theorem that says if a function fz can be written as pz by qz, where pz and qz both are analytic, in some neighborhood of of a point z0. Next, if p of z0 is not equal to 0 and q of z0 is equal to 0, but q dashed of z0 is not equal to 0. That means z0 is a simple zero of the function qz. Then we say z0 is a simple pole of the function fz. And the residue of the function f at the point z0 can be calculated from this expression, pz0 divided by q dashed of z0. Now let us try to apply this theorem. Let fz equal to cot z. Now cot z can be written as cos z by sin z. So this is a function which can be written as pz by qz form. So here, what are the singularities of the function fz? So for this, we equate qz to 0. For singularities, qz is equated to 0, lies sin z is equal to 0. So from here, we are getting z equal to n pi. For n equal to 0, plus minus 1, plus minus 2, etc. These are the singularities of the function fz. So q of n pi is always 0, that is equal to sin n pi, for n equal to 0, plus minus 1, plus minus 2, etc. And what is q dashed of z? That is equal to cos z. So q dashed of n pi is equal to cos n pi, which is equal to minus 1 power n, which is not equal to 0. And p of n pi, that is equal to cos n pi, which is also minus 1 power n, not equal to 0. So all the conditions given in the theorem are true. That is, p of n pi is not equal to 0. Q of n pi is equal to 0, but q dashed of n pi is not equal to 0 for all n equal to 0, plus minus 1, plus minus 2, etc. So here we can conclude n pi for n equal to 0, plus minus 1, plus minus 2 are simple poles. Now, the residue of the point f at the point n pi is equal to p of n pi divided by q dashed of n pi, which is equal to minus 1 power n by minus 1 power n, which is equal to 1. Thank you for watching. If you enjoy the video, then please like and subscribe my channel.